Let's start by a general analysis of gradient descent. How to bound fxt minus fx star. So this is the main question of the remaining lecture. We will use the elementary identity in many places. So this one. This is very trivial equation, right? So for scalar version, we have 2ab is equal to a squared plus b squared minus 2 minus 3. A minus b squared. Okay. So I think you can easily derive this equation. Right. So let's analyze fxt minus fx star from the convex property. When function f is convex, we have gradient of fxt transpose xt minus x star upper bounding fxt minus fx star. Okay, so that comes from convex property. And since the gradient descent approach is xxt plus 1 is equal to xxt minus gamma step size times gradient of fxt, so when we plug in, when we replace the gradient by this one, we have this. Okay, so when we replace gradient by this, we have this equation. And for this, we used this simple elementary identity, this one here. Okay. And the last one, again, we use this gradient descent definition. So we replace xt minus xt plus 1 by the definition of gradient here. Okay, so up to this point, it's very easy, just elementary calculus. So now we will use a very simple trick. I want to add up all these inequality from t equal to 0 to t equal to capital T minus 1. Okay. Then interestingly, this part, look at this. This is plus side, we have t. In the minus side, we have t plus 1. And shape is identical, except the index. Okay, so when you add up all the right hand side from t equal to 0 to t equal to capital T minus 1, everything is cancelled out and only remaining term is this. Okay, and then this term, we just write down the summation. Sum from t equal to 0 to capital T minus 1 gamma over 2 times gradient of fxt norm square. Okay, but unfortunately, in general case, the last iteration does not mean the best one. It's not necessary, so we use the average point. Okay, so we will define x bar, just empirical average, the average of your trajectory, 1 over capital T, summation from t equal to 0 to capital T minus 1 xt. Okay, then from the Jensen's inequality, since f is convex function, we have this inequality, right? This comes from Jensen's inequality. Okay, right. So now we will use ellipsis continuous assumption. Okay, without any assumption, essentially it is very difficult to guarantee something. So So this is the very least assumption. We'll assume that the function value is kind of smooth, so the fx minus fy always upper bounded by Lipschitz constant L times x minus 1 Euclidean distance. Okay, and which means your gradient always upper bounded by L. So from that, when we plug in gamma equal to R over L squared root to T, in the end, we have this one. Why? Why? Because in the previous slide, we have summation t equal to 0, capital T minus 1, fx t minus fx star is upper bounded by 1 over 2 gamma R from the definition of R plus capital T times gamma over 2 times L from the ellipsis continuous definition. So when we optimize gamma to minimize this term, we have this one.